Hello everyone, my name is Yevhen Perehuda, and this is our project with Vlada Homenko, predicting hospital admission of diabetics for class, knowledge discovery, and data mining. Our research is based on a problem that often diabetic patients are readmitted in the future, and if we will be able to detect causal problem, we will save money and improve quality of care in hospitals, to not allow patients to be readmitted again. Our project is based on dataset, namely diabetics, 130 US hospitals, which was collected during 10 years, and it consists of information about encounters of diabetic patient. There are 50 different attributes. Most of them are nominal and 8 are numeric. So firstly, we need to check our data quality and repair it. You can see the heat map indicating missing values in our data set. As we can see, most of weight values are missed, and for payer code the same. So we can just remove this column from our data set. Regarding medical specialty attribute, we decided not to remove it because we read in attached articles to the data set that the main experts recommend to save it because it has a strong influence on patient health. Regarding race diagnosis, race and diagnosis column, we can see that there is just 2 or 1% of missed values, so we can just remove patient with missed values for these features. And here you can see the distribution of weight and payer code values. So let's determine what does it mean readmitted in our data set. We have 3 possible values for readmitted feature. No, meaning that patient will not be readmitted, we transform it to the 0 value, and that patient will readmit more or less than 30 days, and we group these 2 values to 1. And we see that we have an imbalance in our data, but we will manage it later. Now let's do a feature analysis. As we can see from distribution of race feature, we see that most of our patients are Caucasian, followed by African American, and also there are few instances with other races. We decided to group all races except Caucasian to other value. Also, we see that Caucasian have higher probability of being readmitted. Next feature is gender. Here we see that there is nearly equal distribution of genders, and also what we can state that female are a little more prone than males. We can move to the numerical features, and here is a number of applied procedures to different patients, and we see that we see left skewness distribution of data, meaning that most of patients had 0 of number of procedures. Next feature is number of medication. From our data analysis, we saw that most of patient has several medications, and on the graph you can see the readmission probability for them. And as you can see, the more number of medication are prescribed, the bigger probability of being readmitted is. You can ask about number of medication, for example, more than 10 or 20, but as we can see, the confidence interval here is quite big, and that's meaning that probably we really have such trends that the more number of medication patient has, the bigger probability of being readmitted. So what to do with the outliers? We have 8 numerical features, and for each one we have some outliers, and also there is a problem of different scale. And it can cause some problem for prediction, because some models are very sensitive to different scale. So we decided to apply quartile transformer standardizer. Why we chose this standardizer? Because it allows to solve problem with outliers, and it will determine all outliers as 0 or 1. And we can see what our box plots of our numerical features after applying our standardizer. We can see that all scales are equal, and that now we don't have any outliers. After we did a correlation analysis, and what is interesting, we see this correlation between, for example, number of medication and time in hospital, or number of lab procedures and time in the hospital, which is quite explainable, because the more time patient spent in hospital, the more procedures are used for treating him. But there is one small interesting point. We can see that readmitted is correlated with number of inpatient visit of hospital. So probably we need to store information about previous hospitalization of our patients. Next, what we did is we transformed some ordinal data, for example, age and maximum glucose serum test. And the name of our transformation is binning. Regarding age, we can see that we have an elderly population in our dataset, mostly elderly population. For other categorical variables, change or diabetes medications, we just transform encode it to the binary variables. Also the same for gender, where we deleted just three patients with unknown or invalid gender feature. What we can see from after, we can see that for diabetes medication, in case if feature is yes, has a value 1 or yes for diabetes medication, our patient will more probable be readmitted. Also, we removed some redundant data. As we already said, it is a weight and payer code. We removed these columns, encounter ID and patient number, because it just identifiers. And also, we deleted information about sitagliptin medication and hexamide, because for all data instances in our data set, they have the same value for these two medication, namely no. Next group of statistical features, we decided to encode with help of one hot encoding when we transform the value in column to separate columns. We did it with A1C result. This is a test for detecting level of sugar in the blood of the patient. And what we can see here is that if patient has been tested for this level of sugar in the blood, he will have less probability of being readmitted. So if during our boarding of patient in hospital, it's better to check the level of his sugar in the blood. And in case of that, we will be able to prescribe some additional medication, something like that. And probably because of that, such patients who were tested, they have less probability to be readmitted. For medical specialty, we decided not to remove this, despite the fact that many of values were missed. We decided just to group it to unknown value, and we decided to choose just the top 10 of medical specialty, because there were more than 70 different medical specialty, and not to do our dataset too large, we decided to group after 10th position to other value. And what we can see is that patient who had encounter with nephrology medical specialist, they are more likely to be hospitalized again. For diagnosis, we group ID of diagnosis due to ICD-9 codes, and we group them in 10 different groups. You can see the result. So now what we can see from distribution analysis and readmission probability graph, that most of patients had primary diagnosis circulatory disease, and that patient with primary diagnosis blood disease or diabetes disease as a primary one are more likely to be readmitted. For next features, namely discharge, position ID, admission type ID, we group them due to the table which was provided with a data set, and which indicates which ID, what ID means. For example, we see that there are several IDs which are related to discharging to home. So we can just group them into bigger groups. But there is several discharge disposition ID which are related to the hospice, transferring to the hospice, or that patient died. So we can remove them from our analysis. Why? Because there is no sense to check will the person who will die in a small period of time. It's not. There is no reason to make any analysis for them, because they will be definitely readmitted soon. After we did a Spearman rank correlation, and this table shows the p-value of different features and their correlation with readmitted value. And features with p-value less than 0.05 are significant, and we can see quite the same situation as before. The number of inpatient has of inpatient visits has a strong correlation with readmitted value. Also, what is interesting, we matched a number of emergency calls from this patient in the past, and that admission source ID 4 and admission source ID 7 are very significant for analysis, for correlation analysis. So now we're ready to start some prediction, but firstly we need to split our data. We decided to split our data in proportion 80 to 20. We tested also other possible splitting, for example, 70 to 30 or 90 to 10, but 80 to 20 is most recommended for such data sets, and also it showed the best result for the prediction. As we remember, our data is imbalanced, so we have we have two possible ways to manage it: oversampling or undersampling. And we decided to use oversampling, as during undersampling we decrease our we cut our majority class, and it can lead to the some information lost. So we used undersampling, and you can see the graphs of our class distribution before and after oversampling. Now our classes of being readmitted and being not readmitted are equal. We applied 7 different models, namely car-nearest neighbors, logistic regression, naive Bayes, decision trees, random forest, gradient boosting, and neural network. And for all of them, we measured area under curve, accuracy, recall, and precision. And we decided to focus on area under curve as our main measurement. And as we can see, the best results are for logistic regression, decision trees, and the first one is random forest model by this metric, area under curve. We calculated for every model confusion matrix. Here you can see an example of such matrix. And here is the graph of our value of area under curve for different models. And what, of course, we checked our feature importance. As we remember, we have three best models: logistic regression, decision trees, and random forest. But let's check which features are considered the most important. For logistic regression, it was a number of inpatient, admission source in case if it has value for diagnosis, neoplasms, and others. And also, what is interesting, one of the important features was A1C result norm. So it was important. Was our patient tested for this level of sugar in blood or not? For our next model, namely decision tree, we can just, which is also interpretable, we can just plot the created tree. By the way, we decided to do it not very dense, because to make it more explainable and easy for understanding. And here we can analyze our features by importance, starting from the root. We see the most important feature is number of inpatient. So next one is a number of diagnoses. After is admission source ID 4. Was patient admitted from this source or not? And also, for example, there is another important features. Is our patient younger than 70 or not? And in case if he was younger, that means that he is much less is less likely to being readmitted in the future. For our best model, random forest, it's especially harder to find the feature importance because it is non-interpretable model. So we decided to apply Lime methods to find which features are most important and most essential. This method is based on local explanation. So we're explaining each data instances separately. And for example, we took just one random instance, which was predicted as being readmitted. So we can see the probability for 0, namely not being readmitted, and 1. And we see that for 1, the probability is higher. And what we can see, this patient hadn't any inpatient visit in hospital before 0. It gives some weights to the 0 probability. But as we can see, there are many other features which make a big contribution to being readmitted, namely that the patient wasn't admitted from source 4.0. It gives a big contribution to probability of being readmitted. Next one is that patient didn't have neoplasms diagnosis. Next one is that number of emergency call was larger than 0. So before, our patient had emergency calls, and it's quite understandable that he is more likely to being readmitted because he had some problems with health before and worry. And also, we see that A1C result norm is equal to 0, meaning that either patient was not tested or he was tested and his result was larger than 7. And that's why it has a strong influence on our final probability of being readmitted. So we can make a conclusion that firstly, collect patient data on the previous hospitalization. We saw that one of the most important features was number of inpatient visits to the hospital. That means that we should track previous and find information about previous hospitalization because it can has a strong influence on future health of our patient. We need to find and focus also on admission source 4 and 7, which are used if the patient is admitted from another hospital or emergency room, and to review the admission policy and add features related to the policy, so we can more find more detailed information why he was transferred to our hospital, why he was why to not to another one. Next one is that numerical values like number of emergency call for the patient, number of medication, and other numerical features had a huge influence on the final decision. We found it with help of Spearman correlation analysis, and before when we did also when we did feature important analysis of our model, we saw that most of numerical features are in the top by the importance. Next one is neoplasm patient need more investigation. We saw that if patient hadn't neoplasm, he is more likely to be readmitted. So it's also a field for future research. Some features are redundant, for example, payer code, so we don't need to include them into our analysis. Collect data carefully. We remember that, for example, for weight column, most of value are missed. Probably that was done due to some US policy that doctor is not allowed, for example, to ask the weight of his patient. And the last one is that it's important to standardize data because some models are very sensitive to outliers, to different scales. So in our case, we used a quartile transformer, which managed both of these problems. Thank you for your attention. Bye.